So we've got a block on a plane. So remember, it's this guy. I guess I can attach something to it and get. Well, in the interest of moving forward. There you go. Now, when we did this before, we assumed that this was a frictionless surface. But now that we know that kinetic friction is opposite direction of motion, as we move forward, as this thing falls over, there's a tension force in this direction, but a kinetic friction force in the opposite direction. So we're just going to put that in and then work through and see what the solution is. Now, what's known are the masses. We also now have to assign a coefficient of friction to the plane. So we're going to say mu k is here, and that's a known value. Coefficient of friction. And again, we're going to deal with an ideal pulley. We're not worried about that yet. So still ideal. So that the mass of the pulley MP is equal to zero and yeah. So let's just do it then. So we know how to handle this. We take our axis and we place it here. Actually, let me place here. Yeah, so we've got a the center of mass. Yeah, we're just going to do a force in there. So we have tension force there. We've got normal force straight up. got weight down. And on this guy, we've got, actually, this is M1. And here we have M2. And the tension flows straight on. So now, if you assume its pulley is moving acceleration is in this direction for that guy and straight down for this guy. I remember what, oh, and also the friction force, that's the new one. So we got friction in there now, and friction is in the opposite direction like this. Friction, as we said the other day, is always opposite direction of motion or opposite direction of potential, possible motion. So friction. Remember, friction is defined as mu k times the normal force. Now, yeah, and you go ahead and jump to the free body diagram. You know, my point of view is that I place the axis, the XY axis here, define it like that, and then shift it over the guy here. So, yeah. So with the free body diagram, we'll just jump down to that for M1. Well, it's just that, right? It's just going to look like this. That's normal tension, M1G, friction. Just to again remind you, this is Y and this is X for me. M2 is just this. M2, T. And from this point of view, so it comes over. So now Y, positive Y is in this direction, and positive X is straight down. So that the acceleration for both objects can be defined to be in the same direction. And that's the positive X direction. That guy, and A, that guy. All right. So we just apply Newton's laws, right? I like to start here. So the first law in that direction, the second law in this direction, and the same second law in that direction. So from M1, net force in the Y direction equals 0. So that we have the normal force minus mg equals 0. So first result is that the normal force is equal to m1g, m1g. Go ahead and box in that solution. Now before, when we were not doing friction, that was the end of that. But I told you, I kept, you know, I think I mentioned that when we did use friction, we're gonna have to come back and use that result, which is why I always made a point to do it every time, just so we get in the habit of doing it. Now in the X direction for block 1, the net force in the x direction equals m1a. Same acceleration, so I won't put a1 or whatever. It's just, and we know it's in the x direction, but I won't put that there. Now we've got two forces, so let me call on somebody. Arcady, when you look at the x direction here, we've got to do the sum of the forces. And we've got a couple ways we can write it. So you tell me, how do I write that? How do I sum the forces in the x direction for block one?
You can write t vector plus m n vector.
So m is not a vector, okay?
Oh.
And we're just on the left side here. Like m is mass, that's not as a scalar. And m is on the right side. So look at the free body diagram. What forces do we have on the object in the x direction?
A.
A is not a force, that's an acceleration. Come on now. You got it's a free body diagram. And this is the x direction. What are the two forces on that direction? It's like I'm drawing them right here. Let's look at it. Don't guess. Just look at it.
F.
F, yes. And what else?
And R. Oh, T, my bad.
T, yeah. Now, the acceleration is in the direction of what vector? T or F?
T.
T. So if we want to write the acceleration as a positive value, so in other words, since we know that, which magnitude of the forces, which force has the largest magnitude, T or F? And how do you know, Arcady?
T, because it's on its side.
Yes, yes. T, because we know that it's the net force that's giving rise to this acceleration. That's what Newton's second law says. But the net force is a vector sum of all the forces in that direction. What forces are in the direction? You just told me, T and F. So it wouldn't make sense that somehow F is greater than T, but the object is accelerating in the direction of T. That's illogical. So between the two forces, T wins out, and the object moves in the direction of T, which then dictates the direction of the acceleration. It's actually the other way around. The net force dictates the direction of the acceleration.
Mm-hmm.
But when we're working the problem, we kind of go backwards. We can see the acceleration is in that direction. So which force is greater? The force in that direction, or whatever sum of forces that's in that same direction as acceleration. You get it? Get what I'm saying?
Yeah.
Awesome. Good. So then that's it then. So then we write it as a positive value. So we say T minus F equals M1A. Now, you were right about, you said something that I never actually do, but you had a good point. There's actually an interim step to this. I usually just go directly to that. But the interim step is, and you said it very well, T vector, you always will have a plus sign there. T vector plus F vector equals MA vector. That's just the definition of superposition. So it doesn't matter whether they're in the same direction or not. When you're vectorially adding them and you have the vector signs, it's always going to be a plus sign. That's just how, I think some people maybe do it differently, like in different countries, but the way we do it, that's the case. But whenever you relax the vector symbols, you have to put in you have to indicate the relative directions. And so I usually just jump to that point. And because you might see it in books, you might see that interim step in books. So if you don't understand what's going on there, then that's, it can maybe confuse you if you don't know. But I usually jump from the sum of the forces directly to this. But that's good. I appreciate you saying that. It means you've been reading and or maybe you knew what was, knew about that. But yeah, cool. All right. Awesome. So that's as far, well, actually, no, because now before we only had 3 unknowns. We had the tension, the normal force, the acceleration. Now we've got 4 unknowns: the tension, the friction, the acceleration, and the normal force. Well, this equation still is taking care of the normal force. That goes. But now the friction, we got to get rid of that. How do we do it? We use the definition of friction. Right? So that gives us a 4th equation. other than the two that because equally determined. We had three unknowns with always doing these problems. The three equations are the sum of the forces on block one, which is the x direction, y direction, and then the sum of the forces on block two. So that's three equations, three unknowns. Now we've got a fourth unknown, F. Where's the other equation? It's the definition of friction. So we're equally determined then. We can definitely get all the unknowns, mu times n. So to eliminate F, I just substitute the definition of friction into that guy, and then that's done. All right. So 6 into 5, right, gives me that T minus mu k n equals M1A. But now now I've got the normal portion and I got to get rid of it. But I have this guy. So now I substitute 3 into 7. So then T minus mu k M1G equals M1A. That process is going to be standard for all the different problems. So now that we've developed this pattern, this way of addressing these problems, our technique is solid. It's inherently in there. And so we've seen a subtle change because we didn't have that before, but we can handle it. So cool. So now we're back to the two unknowns that we had, we always have with these kinds of problems, which is T and A. And we've exhausted everything for block one, which means now we go to block two and we apply the second law there, and we can get it. So what I want to do is this: since you guys are, or you students are kind of, yeah, why don't you go ahead and do that? I know I need to go get some tea real quick, and I need to also use the restroom. So go ahead and work on that. Apply the second law to this guy. See if you can go ahead and try to find, at least get as far as getting the analytical solution for the acceleration. Again, I'm going to do both, and we'll compare it back to when there was no friction on the problem to see that it should reduce back to that solution. Go ahead and keep working on that, and I will be right back.
We can't hear you, Professor.
We can hear, but it's really like quiet.
I don't think your AirPods are connected. We still don't hear you, Professor.
Testing, testing, testing.
It's good now.
Good. I think I had to reset somehow. All right, so good. Okay. So we're gonna do block 2 now. So for block 2, again, same thing. Who did that just was that who was that was just asking me told me that you couldn't hear me?
It
The
was
last
me.
person. Oh, Kareem. Yeah, you want to take this one, Kareem?
Yeah, sure.
Yeah, go for it. How do I apply Newton's second law to this guy?
So
How do I evaluate the left side? So-
the magnitude, the forces of X is gonna be 0, right? Because we're just moving the second block vertically.
Remember, X is down, like when I shift it over, X is down and Y is to the right. So Y is 0, the way I'm doing it. You know what I mean? Like when I shift my axis over, like this is the X direction. So when I go over the pulley, X is down and Y is positive, Y is to your right. So I believe in that case, we would say that the forces along the Y direction are 0. But yes. You follow me?
Yeah. So it's just the normal applied force, wouldn't it be, right?
What do you mean the normal applied force?
I'm talking like the applied force that's given to us, or the force that you apply to move the boxer. So would that be the applied force times the cosine of the angle?
Where are you looking at? Like we're at this problem. There's no angle. There's no. What are you talking about? Look at block 2. What forces are on block 2?
the M2G, and the tension.
Okay. So what cosine are you talking about? What are you talking about?
I was just trying to, I don't know, I was just looking at the tension.
Okay. So again, you look at the tension, where are you getting the cosine of an angle from? What angle are you talking about?
How
So
would we
try
get
to,
the tension then?
well, we have to solve the equation simultaneously to get the tension. That's what we're doing. Right now, though, what I'm asking you to do is to apply Newton's second law. And in doing so, you see that equation that says F, the net, forces in the x direction equals M2A. Do you see that? It was, I'm away from the board now, so I forget what number. It's number
Equation number
9. You
9?
see? Yeah. You see
Yeah.
that? That's what I'm asking you to do right now. So to answer your question specifically, look at equation 8. You see in equation 8, what are the two unknowns in equation 8? I have them underlined in green.
The tension and the acceleration?
Yeah. So those are the unknowns. We don't know what they are. So you just asked me, how do I figure out the tension? Well, that's one equation. I need another equation that has tension in it in order to solve simultaneously. That's how you figure out what T is. Do you understand that?
Yes.
Now, I have exhausted all of my information for block 1, so there's nothing else I can do with block 1. But with block 2, I haven't done anything. And the one thing that I can do is apply Newton's laws to it. You correctly assess that along what I'm calling the y direction, which for block 2 is the horizontal, there are no forces. So that's out. There's nothing to do there. In the x direction, which for block 2 is vertical, it's accelerating along the x direction. So I can apply Newton's second law. Understood?
Yeah.
So that's what I'm doing. And in the process of that, I'm at the point where I'm asking you, now that I've applied it there, I've got to evaluate the left side, meaning the net force side. And so I'm asking you to do that by looking at the forces on block 2 in the x direction, just like we did for the x direction for block 1, and tell me what the sum of the forces looks like for block 2 in the x direction. Is that clear?
Yep.
Okay, so do that right now and tell me what I should write for equation 10.
Would it just be tension minus M1G or M2G?
Okay, possibly. Can someone chime in and tell me whether they agree with that and then give a reason as to why or why not? Anyone? I'm not at the board. I'm getting my tea. So just,
I would say I would agree with that statement.
that was
And
who was that? Who was
that's
that?
Mikey.
Mikey, yeah. Okay.
Yeah. And my reasoning for that is because since the acceleration is going or like I guess since like block 2 is moving downwards,
Mhm.
that to me means that M2G has to be greater than T.
That's correct. But that isn't what Kareem said. Kareem, repeat again what you said.
I said for the left side, it would be T minus M2G equals M2 times the acceleration.
That's right. So now, Mikey, did you listen to what he just? Because you probably, in your head, you probably said, what would you say, Mikey, based on the point that you just made?"
Wait, what do you mean? Like, wait, I'm kind of confused now.
Okay, maybe I need to write it. This is what it's Kareem, right? Kareem was talking.
Yeah.
Yeah. This is what Kareem said. He said T minus M2G equals M2A. But Mikey, you just said you agreed with that, but then you said that M2G is greater than A. Well, that's
I said M2G was greater than T. And
yeah,
the
greater than T. Yeah.
attention force. That's why I said like originally. Is
Yes.
that not correct?
It is correct.
Oh,
Yes,
okay.
that's what I'm saying. M2G is greater than T. But
Okay.
that's inconsistent with the convention that we've been using for the equations. Look what he wrote.
So is it M2G minus T?
Yes. Yes.
Okay.
Because if you write this, you've introduced a mistake. Because it's implying that T, basically this quantity is negative. So if you want to stick with that, you have to put a negative sign over here.
I see what you mean.
Because otherwise you've said that the accelerations are in the opposite direction, right?
Does that
You
mean the
implicitly
object,
said-
that mean the object is really flying in the other direction, if that's true.
That's what this means. Yes. Yes. That's what that means. Because you're
Okay.
saying that they're the same problem, you know, because we're going to equate these. We're saying these are the same acceleration, but they're not. The way you wrote this acceleration is the negative of that. So you have to explicitly put it in.
Okay.
I don't like to do that. What I like to do, and it doesn't matter. You can do it that way if you want. But what I like to do, and what I teach, is just always write the acceleration so that it's a positive number. That's one way where we don't have to, because I'm terrible. And I shouldn't repeat it because I reinforce it by saying it. But historically, I miss negative signs and things like that. So I've worked out something where I miss it less like, and for me, I'm very intuitive and a visual person. So when I'm looking at this, and that's why I make the point, because I think it kind of confused you a little bit, maybe because you don't like to see it. When I talked about how I'm doing this coordinate system, and I'm talking about that's why I do that. Because like here, the coordinate system, this is the X direction, right? This is the Y direction. For me, even though this is going down, like mathematically, it's got to be the same direction. So I kind of just think of it as translating either I could take this thing and scroll it up and just think about the problem moving along in the same direction, or I could just, transfer the core, because I can do that. You can do that. The system over, and so now that's positive X and this is positive Y. I mean, the tension is going over, like you can do that. Mathematically, you can do that. It doesn't change anything. So I see everything going in the same direction, and I'm calling that the positive direction. So now I'm going to make down the positive X direction. That's got to be inherently positive. So I subtract the largest force in magnitude from the smallest force, and clearly that is the largest force. Why? Because it's going down. If P were larger than M2G, then it would be going up. So just by writing it as M2G minus T, I'm making this number an inherently positive number. So I don't have to worry about thinking about putting in the negatives. And for me, it's just faster. Otherwise, I got to think about it, and then I might make a mistake and whatever. So this guy is faster. T is greater up here than this guy, and down here M2 is greater than T. Why? Because they're all moving in the same direction, which I'm calling the positive X direction. Does that make sense?
Yeah, that makes sense. I honestly didn't realize that M2G is actually greater than T, but then I looked at it again. I was like, yeah, M2G is actually greater than T because it's going downwards.
Yeah, yeah. It's okay. That's why I like to do these problems, because we did say that, last week, but it was simpler, right? Because I didn't have a force over here and whatever. We talked about it. You can go back and look at the lectures. It came up. But there's so much going on. There's so many moving parts that, it takes a while for everything to sink in, which is why have teach this section, spend 3 days on it and teach the second one and just keep going back over them and making them a little bit more complex, right? Because these things start to kind of sink in and make sense after a while. I've had a lot of success with that. So yeah, cool. And Micah, you see why you were correct, but you were looking at the equation, and the equation wasn't consistent with what you were saying. Do you see that now?
I think I do. So okay, what you're saying is that for whichever like vector has like the greater magnitude, I would have to list that vector first in the equation. Is that correct, or is that just true for this instance?
It's true if you want to write the resulting acceleration as a positive number, which is what you're
Okay.
implying, which is what you're implying when you don't put in a negative sign,
Okay.
right? That's the convention. Go ahead.
Okay, yeah, that makes sense now. That's the only thing that I was confused on, so that just like cleared up my confusion, so yeah.
Yeah. And that's what we assume. When we don't have a sign, we assume the thing is positive, right? Yeah.
Yeah,
So it's not that what he said was wrong inherently. You could put t minus m2g, but that whole number is negative. So because we are making positive implicit and negative explicit, then you have to physically go over and put a negative sign. And you see it's the same equation though, right? If I write t minus m2g equals negative m2a, well, if I multiply it through by a minus sign, what do I have? That's going to be positive, and this is going to be flip around. So I might as well just do it in the first place. Because for me, it's more organic to do it that way because of the reasons that I was just talking about. See? Everybody see that?
Yeah, that's true. It's less negatives to deal with.
Yeah, it's less negatives to deal with. That's all. That's all. And the whole reason this whole funky thing, I know it's funky because everybody gets quiet when I talk about it. Like, what the heck are you doing? The reason that I created this thing, this little mathematical process with the coordinate system is because at some point it came up, right, in the class. This was years ago. If I come over here and I just redefined it, because it doesn't matter. Like you could call this positive y down here. Like you could keep the y up and the x horizontal. Well, that doesn't make sense, right? Because how can this? Because we're saying that a is the same, but it's a vector though. So it's not. It can't just be the same in magnitude. It also has to be the same in direction. Otherwise, it's not the same. So, and we're going to end up equating the equations. That's what we're doing. Because you talked about initially, was it Karim, about solving for t? Well, now we can solve for t now that we've got this equation correct, because this is the second equation that we need in order to solve simultaneously with equation A. So we got unknown t and a. So we're literally saying that those vectors are the same in magnitude and same in direction. Well, you got to be careful because the forces aren't necessarily, their magnitudes are the same because the forces are on two different things, right? This tension, even though it's the same magnitude, is not the same tension as that because it's on a different object. But this acceleration is the same as that because that's the way acceleration works, right? When you have something connected like that. So you got to be a little bit careful about that. But even in that, it's kind of working out because we're seeing that negative sign. If you kind of think of it in terms of that tension, one is negative of the other, right? And that, so and again, it's just brilliant, like how it's one thing to, in retrospect, have these laws and then work them out and then start to see all these little things. It's a whole different thing, before Newton did this. Like how, I don't know whether he thought about all these details in retrospect or maybe he had some insight and then just, tried it and then saw that it worked and all these other things worked out. I don't really know, but it's insane. It's insanely crazy how magnificent these laws are and how simple they are and what you would do. Like, how did you even, thousands of years we went and we didn't have that, at least as far as we know. So, it's not like an easy thing. It's incredible, even though now it just seems kind of simple and just a matter of figuring out how to use them appropriately. Still, it's pretty incredible. Anyway, so let's move forward.
Oh, Professor, isn't
Yeah.
for equation 10, isn't it supposed to be m2g minus t? Or
Yeah, thank you. Sorry.
okay.
Thank you. M2G minus. Yeah. Cool. Yeah, so now, Kalim, also you realize, that M2G is great. It was in all the other problems before that we did. This equation doesn't really change because the friction up here, and that's another thing, like the friction does affect it, but it affects it through the acceleration. But again, you don't have to worry about what's going over there because friction is not applied to this. It's just these forces are applied to this. And somehow all the other attributes implicitly that are affecting that motion is going to be in the equation. It's going to be in there. The information is in there, basically connected through the acceleration. But you don't have to worry about anything else. All you got to worry about is the kinematics and the forces and the dynamic associated with that object. And if you do that right, then when you put everything together, it works out. Again, the brilliance of the laws of motion. You know, hindsight is 20/20. But if you're trying to figure this stuff out, like, you know, because you might be tempted, like if you didn't know, I know there's a friction over here and it's affecting this motion. So how do I put it in there? You know what I mean? If you really start to think about it, it's not an easy thing to figure out that these laws work. You know? Anyway, they do. And so we don't have to reinvent the wheel. We just have to use it now. And that's why everybody makes these comments like, like Einstein said, I stand on the backs of the people like Newton who came before me. This is what he's talking about. Yeah. Anyway, let's keep it going. So yeah, so actually the physics is over. The physics is done. At this point, it's just math now, right? It's just algebra. I think it's important to point that out. So we can do the same methods we did before. Like what I did, I think I just added the two equations. That's a really simple, it eliminates a couple steps. So go ahead and do that. Add the two equations and solve for A. And I'm gonna go ahead and finish up with my T here. And then if you get that really quickly, then take that and plug it back into one of these and get T as well. And I'll be right back. Oh, I knew what I was going to say. So Kareem, so I was kind of messing with you a little bit because I knew where you were getting those at an angle stuff from. But I just wanted you to become self-aware, which is why I asked you the question. But you remember on the first day how I told you that we're so used to learning by rote that it's hard to break out of that habit, memorize problems and apply them to the other thing. Where you got that stuff from is all these other problems where we did, and I got the angle on there. So whenever you not you, I mean you as the universal you, whenever we start to get confused, even as we start to break out of the habit, the tendency is to go back to old habits, right? So because we had been doing a lot of these problems on angles, and there's angles in there, then and you the tendency is try to want to memorize those previous solutions and apply them to this thing here. So that's where I know that's where you got it from, right? But again, it just takes a while to break out of the habit because the angle here, that angle that you're talking about, is the plane angle, and the plane angle is right here, and it's zero. It's zero relative to the horizontal, so there's no plane angle, right? It's not going to map up. But now the next problem I am going to put it at an angle above or below the horizontal, and then we'll do the problem again, and you'll see that it'll start to come through again. So that is the tendency, right? It's just a strong tendency to break because we've been ever since kindergarten. We started. You learn by rote, right? And so it's hard to break that habit. But that clearly you can see that, I say that a lot. I'm not a psychologist or a sociologist, but I can think, and I'm a physicist, so I see these patterns. And now that you understand what to do, you can see how your answer makes no sense, right? Because there is no angle here. So that's how I know what you were doing. Does that make sense?
Yeah, that's true.
Yeah. So, but I just want you to, and it's not a critical, it's not a bad thing necessarily. I mean, but I'm just trying to make you self-aware because again, the whole point of this problem solving technique and the big thing with physics, it's not just about getting the right answer. It's not. Trust me. It's about how you're approaching the problem, meaning what you have control over is the process by which you're thinking, your thought process. How am I thinking about the problem? How do I think about physics problems in general? What is my technique for applying my thought logically and correctly, given a set of theoretical concepts? How am I applying that theory to the problem? So, it's called metacognition, thinking about your thinking. So, I just want to continue to point that out when it pops up, because you reverted to something comfortable when you didn't know what to do. And what was comfortable is just trying to find the equation that I use for some problem like this that might, and so that's, the more we become self-aware, the more we are less likely to make those kinds of errors. Right? So just wanted to point that out to you. And that might not have told you what to do, but it certainly would have told you what not to do. And the more you become aware of that, you become confident in that.
You heard, Professor?
I'm here, yeah. Mhm.
I was just trying to say, one of the things that I felt like really helped just kind of distinguishing the forces in terms of X and Y is when I have like two blocks on a pulley, the block, like the second block, I try to move it in the same direction as the first block. So I like literally draw it upwards where they're in like a straight line, just so I can like distinguish really the forces between X and Y and not make mistakes on that.
You know what? If you want to do that, that's fine. I think that's what I was alluding to. You're saying like it's like taking two and swinging it up so they're moving along a straight line like this.
Yeah, exactly.
Yeah, you can do that. That's fine. If that's how you want to think about it, fine. Go for it. Go for it. This is just how I think about it. Like that. And again, I always say there's like an artistic element, an artistic aspect to science. People don't realize it, right? Like because you think science is so exact and everything, but it's just the way that you interpret and figure out how to do things are based on your own sensibilities. It's just like when you're looking at something like The Voice or whatever, and they say, you're making an interpretation of the song, but you got to make it your own. Actually, everything is like that, and art is like, and this, even though it's science, and we make a distinction between art and science, art is about creativity. So, like I said, when Isaac Newton, when he was looking at the universe and looking at blocks on a plane and trying to figure out the relationships, it's creative. There's a creative impulse. You got to be, that's how he's coming up with this stuff. You're just guessing based on your intuition. But your intuition manifests from person to person with little differences. And this is for everybody, to the class, little differences about what Kareem said. That's perfectly valid to do that. And I think I mentioned it earlier, right? But I just don't like. For whatever reason, I don't know. I like to think of the x-axis going on and doing it like that, as opposed to flipping this up every time and doing that. It's just a slightly different perspective, but it's not wrong. And if you become a physics teacher and you teach someone that, you may do it like that. You may teach them to flip the thing up in their mind and then rewrite it along there and then have their whatever. That's fine. That's fine. So once you start to do that, though, reason I'm spending a little time on this is that when you start to make these little changes based on, like, I'm presenting it to you in a certain way based on my sensibility. But as you begin to tweak it and change it based on what you like to do or how you think, that would be the equivalent of making this song your own, or making this process your own, in the same way that they talk about on some of these singing shows. And that's fine, because once you do that, that means you're starting to really incorporate it within your sensibility, and you're starting to understand it, right? And you're starting to become creative based on you. So that's a really good sign. That's good. So everybody, that's for everybody. When you start to see these things, there's no necessarily right way. It's only right, like in the movie Oppenheimer, when you get the right answer, and experiment shows you that you got the right answer. That's what tells you whether you're right or not because somebody else did it this way and got the right answer. So, because there might be many ways to do it, and those different perspectives, again, because what we're seeing here in this universe, and the way this, in the three-dimensional space-time universe that we can see, it actually might be a reflection of more general properties that we can't really see in higher dimensions. In fact, most people think that is what the case is, that now that we're kind of making some progress with quantum mechanics and the implications. Just in the same way, this shadow is a component in 2 dimensions of my three-dimensional arm. And when you look at the shadow, there's a whole lot of information that you lost. So if you just are looking at the shadow and trying to figure out the physics of that, well, you're at a loss, because you can't see out here. Everything that we can see around us is like that for higher order dimensions, right? So I got on that because it's important not to suppress a different perspective. Some people do that because, for whatever reason, power plays or wanting to maintain control or whatever. But I teach that you want to encourage your sense, and you could be wrong, but if you're wrong, you just fix it when you know you're wrong. And every time you're wrong, whatever is right, you just learn it better, right? So I encourage you to look at it in different ways, or whatever, however your sensibility is, because that means you're making it your own, and you're really beginning to understand it on a deeper level, it being the whatever concept you're using, or whatever process or protocol you're trying to apply to a system. Does that make sense?
Yeah, that makes sense.
Yeah. All right,
I
cool.
just want to say, I don't know if you have your camera pinned though.
Camera what?
I don't know if you have it pinned, because you said you want to make sure it's pinned, so when people watch the recording back, just
Oh, thank you. Yeah, remind. Yeah, it's pinned. I have the camera pinned. Yeah, thank you.
Yep.
So it's still a switch back in the green, but I can tell because on my screen stays clear, stays open. So it's pinned.
Okay, cool.
Yeah. Thank you for reminding me of that. All right. It's time for the break. Oh, let's go ahead and knock this out. So I'm going to add the two equations. 10 plus 8. Tension will cancel out. I'm going to have M2G minus mu K M1G equals M1A plus M2A. Factoring out the G and the A, I get G times M2 minus mu K M1G equals A M1 plus M2. Dividing through by the total inertia of the system and solving for A, I have that A equals G times the ratio M2 minus mu K M1. Oh, so there should be no G here. Divided by M1 plus M2. There you go. And if you compare that with our previous solutions, sure enough, you can see it here. When on the previous solutions, it was a frictionless surface. Well, frictionless surface, the mu K goes to 0. Here's my thing. The mu K goes to 0. And under that limit, the solution goes back to G times M2 over M1 plus M2. And that is correct. That's what we got before. That's what we got before when we had a frictionless surface. So, and also you see that you would assume that whenever you make mu K non-zero, it's going to cause the acceleration to lower the acceleration because you got something working against the motion. And sure enough, you can see here that it does because the original acceleration is mg times m2 over m1 plus m2. But in the numerator, you're decreasing the numerator by a factor of mu k times m1. So clearly that acceleration is going to be less, or this acceleration will be less than when mu k is 0. So it makes sense. Okay, just for the purpose of illustration, now again, you could just take A and plug it back into the value A and plug it back into this thing to get the numerical value T. I'm going to do something a little bit more than that in the class just for the purpose of illustration. I want to get the analytical solution for T because only from that can we evaluate the physics of what's happening. Now, would you expect that? Now, you tell me, would you expect the tension to get higher or lower by adding friction? And why or why not? Anybody? Like the value of it.
I think my intuition says that if the value of friction is increased, then the value of tension would decrease because then friction would have a greater magnitude than it did before.
Okay, let's go with that for a minute. Let's do a thought experiment. Let's do a thought experiment. Now, Mikey, let's say that you and I are playing a game called Tug of War. Remember that one from when you were a kid?
Yeah. Remember when I got dirty?
All right, so let's say that as opposed to just having the rope between us, we make it a little bit more complicated where, so I'm on this side and I'm pulling right now and I've attached the rope to the box. So right now, the thing that I'm working against when I pull the block is the inertia of the box. How, its mass, how large it is. But now let's say that, and so forget friction. Let's say it's a frictionless surface or whatever and whatever. But forget friction for right now. So let's say that you come along, and now remember the tension in the string is based on basically the amount of mass, the inertia of the thing, the inertia, since it's frictionless. And it's true, like the larger the mass, the more it will be harder to start because of the first law of inertia, and because of what mass is inertia. Okay. But now let's say that you come along, Mikey, and you grab the other string over here, or you attach a string, and you start to pull in the opposite direction. What will happen to the tension in my string when you do that?
The tension actually increases, right?
Yes, it
Okay.
increases. Okay. All right, good. So now let's put that thought experiment back down and go back to friction. When there is no friction there, the tension force is just working against the inertia of the block of the block one in the same way. Now there's no person over there, but it's friction, and friction is in the opposite direction. So when you do that, when you're pulling in the opposite direction, what again? Just to be complete and finish this out, now what would you say based on that analysis and that thought experiment? What happens to the tension in the string as friction increases, in your opinion now?
As friction increases, tension would increase for this problem.
I agree. At least. And we give it that there for now. And you perfectly fine to evaluate every time. You don't take anything for granted. Every time we do a problem, just reevaluate, and I'm good with that. But yeah, so I would agree. That's what I would agree with. Now, we're going to solve for the analytical solution for tension. If we get an analytical solution that does something other than that, increases tension, then maybe our intuition was wrong. We have to go back and reevaluate it. But this is what I'm expecting right now. And so I'm expecting to see something like that compared to the original solution for when mu k was 0, that of the tension equation that we got before. Okay, so that kind of analysis, that's what physics is. And that's why I like to get the, because I think we had a discussion with some student a couple of weeks ago about why I go back and do that. I think they were saying you could just go back. Well, you could, but that's not going to tell you any physics. That's just going to tell you what the value of the tension is for that particular problem, which is fine. But if you want to know something about the physics, because you might, because it's a physics class, or at least I would, then you got to go back and you got to look at the analytical solution. So these are the kinds of things that we're looking for, that we're comparing, and why we do that. All right, so let's do it. And you got a couple of options. I'm just going to take what looks like the easiest. I don't know. It doesn't. They're both about the same. I might stick it in here though. I might stick the A in this guy. Probably do that. Yeah. I'm going to put A into so 13 into 10, and then just do the algebra and see what we come up with, and then compare it to the previous thing we got. You can work along with that if you want. Yeah. So 13 into 10. So we're going to have M2G minus T equals, so that's going to be, well, I'm tempted to do this in steps, but I won't. So I could just we'll put it in and then we'll multiply. So M2 times the quantity A, but A is G M2 minus mu K. I think I did that before and then had last weekend. Somebody didn't see it. Okay. So now on the right side, we're going to have G, and we'll have M2 squared minus mu K M1 M2 over M1 plus M2 on that. Now that I'm going to take over. So now if I take this over, this is M2, this is this thing minus M2G, but I got a minus sign here that I got to translate through. So if I translate it through, I'm going to have T is equal to M2G minus G times all of this stuff. M squared minus UK M1, M2 over M1 plus M2. But this is M2G over 1. So now I got to add them with the common denominator. And the common denominator is M1 plus M2. Okay, so finding the common denominator, equation 17. So I'm just going to write M1 plus M2 in the denominator. Now, essentially, I'm multiplying M2G over 1 times quantity M1 plus M2 over M1 plus M2. So you get the common denominator, but then you got to multiply through and you get two terms out of that. And also, I'm going to factor the G out of each term. I'll do that right now. So the G will be over here. And so I just have all this stuff in brackets. So the two terms I get out of that thing is going to be M2 times M2. So it's going to be M2 squared. And then plus an M2 or M1 times an M2. So those are the two terms. And then I got these two terms left. So it's, and don't forget this minus sign out here. So I multiply that minus sign through, I've got a minus M2 squared, and then a minus and a minus is a plus. Plus mu k M1 plus, or M1 times M2. Okay. The M2s go out and two squares go out because of minus sign. And I have G times quantity M1 plus M2. And up here, I've got M1, M2 minus UK M1, M2. Now, there's one other step on the right of that first. But for now, let's just pause and take a look at that. Now, again, whenever, this is a plus, so that should be a plus. But also because of what I just said earlier, a few moments ago. Look at this. When mu k is 0, this whole term is 0, and this solution reduces to G M1 M2 over M1 plus M2, which is the tension with the friction 0. That's what we got last week when we did this project. We did it last Wednesday for the first time, a week ago. And also, look, there's a plus sign here. So it means that what we just said, I'm increasing by adding the frictional term, I'm increasing the denominator by a factor of mu k M1 times M2. So our intuition is correct that when we, well, your second intuition, Mike, after I've guided you a little bit, is that as the frictional force increases, and how will it increase? Well, the normal force clearly is not going to increase. Well, it could either a couple ways. It could increase, the normal force could increase or decrease depending on the angle, or keeping the angle flat. The only way to increase the frictional force is to increase mu k, because that shows that either way we're increasing that term. So as the frictional force increases, the tension increases. That's what this equation is clearly saying, and it's a fundamental inherent property of the system. Well, I like to simplify a little bit more. I can factor out the M1, M2. So if I do that, I'm going to get G times, and I have this factor here, M1, M2, divided by M1 plus M2, but then times this factor on the outside, 1 plus mu k. And I like it like that because it's more, it can more easily evaluate the thing right at that point. That, again, you can say the same thing, the friction force increases because I'm multiplying it by this factor of 1 plus mu k. And whenever mu k goes to 0, then the tension force goes back to G times M1, M2 over M1 plus M2. Oh, God. I guess it's break time now. We're over a few minutes. Any questions, problems, troubles, and or gripes? Why don't we make this a working break? I think you're making some progress here. You're learning something. I can feel it by the way that you're responding. So I like to kind of keep on top of whenever we have these spurts. So you can take a few minutes, but let's make it a working break. And I'm going to go to tweak the problem a little bit, just like I did before. Now, I can't remember whether I took angle up or angle down. It doesn't matter. You can tell me. Do you want to go angle up or angle down? So we're going to now put it at an angle. Your choice. Putting block 1 at an angle relative to the horizontal, up or down, above the horizontal or below the angle. Anybody?
I don't know. Let's do below.
Okay. All right. Mikey spoke up, so he gets his wish. So that would look something like this. Okay. Now everything that's given now is so M1, M2, theta, which is here, and also mu k, the coefficient of kinetic friction on the surface. Remember that we like to place our x-axis so that it is perpendicular to the plane. That's y and that's x. Flipping over, still we have y to the right and x down. The way I'm going to do it, you can do it a different way if you want, or think about it in a different way. Okay, so that's all you need. So what I want you to do is find the system tension and the system acceleration in terms of given quantities. Find T, analytical formula for T and A. So you apply the forces, and there are 4 forces again: gravity, normal force, tension, and friction. And you apply the forces on block 2, tension and friction, or sorry, tension and the weight. I said normal force? Oh no, I said normal force, tension, weight, and friction here, tension and weight. And then see if you can go through and at least get to solving for it. You can take 10 minutes, 15 minutes, then come back and work a little bit, whatever. But see if you can apply that and get all the way to getting the acceleration of the system. And then proving to yourself in the limiting cases, in the limit as mu k goes to 0 and theta goes to 0, does it reduce back to these solutions that we've gotten? If so, you got it right. If not, there's an issue somewhere. Go for it. So let's take, what time is it? 40, 42? And we'll come back, probably a little bit, maybe 5:10 or 3:10 or 3:05 or 3:10. We'll give about 25 minutes. I want you to work on that a little bit, see if you can make some progress on your own. And think about it before I give you the thing. All right. So how you feel about this so far? You feel like you're understanding? Somebody give me some feedback. How you feeling? Trying to make some sense with Newton's laws with these problems?
I think right now it's starting to make sense, but I feel like the only way like I'm gonna truly know if I like actually get it is just to work with it. So
Yeah.
but I'm feeling pretty good so far though.
Well, hi Esperanza. I see you're here in class. Did you see that note that I posted this weekend about the stuff that I did do some extra an actual addendum lecture, and I'm gonna probably post 2 more, at least 1 more. Because I didn't get to drag. I just got to doing the problem we did last week that you were working on. Did you see that?
I did see a notification, but I was not able to look at it yet.
Okay, no worries. It's there. I haven't posted it in the week. I'll do that today. But because it takes a day or so to process. But I will also include my notes on the page. So my notes are pretty comprehensive, a lot more verbal explanation about what's going on in each step. But I did, derive it on the board and everything, and so it's there. So you can take a look at it. And yeah. All right, cool.
Yeah.
Try that again. What about now, Mike? You can hear me?
Yep.
Awesome. Did anyone get a solution for A? For this last one? This guy here? Nobody? Gave you a few extra minutes there. Hoping somebody would come up with it.
Well, I got an answer. I'm not sure if it's correct though. Actually, I
Tell
don't
me.
think it's correct, but I got okay. So sure, I'm eating on something.
That's all right.
A is equal to G parentheses M2 minus mu K M1 cosine theta. All that over M1 plus M2.
Why do you think that's not right?
I honestly, it just seems so like closely like related to like the last one. And I think I'm kind of like second guessing myself, but to me it makes sense because the only thing that's changing in this problem is the angle at which like the block or mass one is sitting on. So yeah, I don't know.
Cool.
I guess I'm just second guessing myself.
Well, that's good. And I go, is Kareem still in class? I think he must have left. I don't see him anywhere. But yeah, but he had talked about something about the angle before, but there was no angle before, right? And so there was no reason to think that there would be an angle associated with the solution anywhere or whatever. But once there is an angle, your deduction is correct, right? Because there's an angle associated with M1. It has nothing to do with M2. So if you see it manifest, you would think that it would have something to do with that second term because that is the term for the friction. right? Now the tension force too, like, but it was along the x direction. The tension force remains along the x direction. The only thing that you get are components along the x and y. So yeah. Did you were able to go ahead and get something for so you said M2 minus mu k M1 cosine theta, right? That's what you said?
Yep, that's it.
Okay. Yeah, I think that's probably right. Because remember, because what's going to happen is, so I've multiplied through by G or factored out. But remember, the normal force is, friction is more normal force, is mu k times N. Now, when it's flat, the normal force is just mg, it's just mg. But when it's not flat, you can going to see it here that there's going to, the normal force is going to have a component along the y direction, and that component has been consistently mg cosine theta. So you can see the normal force right in there. It's g times mu k mg, well, mg mu k sine theta. It's mu k times the normal force, but the more normal force now that's on the plane is going to be mu k cosine theta. So I think that's right, and it is minus, right? You did get minus because it shouldn't be plus. Because all right, actually it should be plus, not minus. Is that what you said?
I said minus. Is it plus?
Well, you would think that when you bend down, let's see, let my intuition off. When you bend down, oh, the acceleration, right? Yeah, the acceleration is, no, I think the acceleration's got to be greater, right? Because, well, actually, what? Actually, I don't. Compared to, yeah, I think it's got to be plus because now, so when I'm flat, the friction takes, well, no, maybe you're right. Yeah, minus, right? Because it's going to be even, yeah, sorry, I'm sorry. It's going to be even more, it's going to be even less. So it increases by sine theta. No, you're right. It's still minus. You're right. You're right. Yeah, sorry. Brain part. Because it's opposite the direction of motion. Yeah, did you get something for tension? So the tension is going to increase. So acceleration decreases, tension increases. What'd you get for tension? Did you get that yet?
Well, I didn't get like a fully like simplified answer. I was kind of still in the process of doing that. I think I'm kind of close though, but it's looking like my answer is kind of long-ish, sort of.
Okay.
I can hear. I'll just tell you what I have so far. It's
Okay.
you're gonna have to bear with me here. So I got M2G minus T is equal to M2 squared G minus mu K M1 M2 G cosine theta, and then all of that over M1 plus M2.
I think that's right. So now you just have to find the common denominator with that in the first term that you mentioned, right?
Yeah,
Yeah.
that's what I was working on.
Yeah. Awesome, dude. Good. Good. Very good. Yeah, I think you're getting it. Yeah. So for those of you who did anyone else get that far, or just want to see a show of hands? Okay. Well, let's go through, and this is the last one I think I'm going to do in class. I'll post some, like, I've been starting to put like addendum lectures, and maybe I'll do like a couple of the others in addendum lectures, but I want to keep it moving in the class. So I forget what's next. I have to look at my notes. I think we have to do some other things in this chapter before we move on. Yeah, you could. There's a couple of types. This is just one type of problem, but this is like the base foundation types of problems I like to do till you get to this point where you can apply the things correctly. But we still got centripetal acceleration, the force, putting other things that we can talk about. So I want to do a couple of problems like that before we applications before we leave the chapter. I think this is chapter 6. But I'll keep it going at a pretty good clip because I think, we got these courses. There's so much material packed in. So we got to keep it moving on. So this is the third day we spent on Newton's laws. And I know it's 2 chapters, but they just break it up. Some books is 1 chapter. but it's appropriate amount of time. Right? You know, it's foundational. So if you can get this, you know, at least understand what's going on, even if you have to practice, then you don't want to leave this section without having a pretty solid understanding of how we're doing this. Whew. Okay. So I was just looking at the, I had to say something about it, the news. And there's a new war we got going on now in the world. Um, free body diagrams. Well, before we do that, let me just go ahead and draw in the forces here. So that's M2G, M1G straight down. M2G. Sorry, M1G. So what am I saying? I'm having a brain fart. Sorry. That's T, tension. Dirty. News in my mind. About the fate of the world. In and what's the frictional force down the plane? So we'll call that F. Frictional force F. Actually, I think you missed a force. I think you missed something. I think there's got to be 3 terms up there now. So there will be that F, but I think you missed something else. So I'll show you. Yeah. All right. So of course this is theta here. Theta. Well, you know, this is theta here, but it's also you go through and show that this is theta. So when we do the free body diagram for block 1, we're going to have normal force up. We're going to have straight up. At 9 degrees, you're going to have T there. Now you got the frictional force there. But now I have to show you here, and so make it clear, this is why I just called it. Here we've got a component mg cosine theta here, or m1g cos theta. But you also have a component of the gravity along this direction. So you got mg sine theta there, okay? Now, I'm gonna draw that up here. That means, with these colors, you got m1 G cos theta here. But now this is a separate force that's also along the negative x direction. It's separate from friction, M1G sine theta. So now you've got three forces along the x direction. And the reason I think there's a problem is because you only had two forces.
Yeah,
Your
I
acceleration.
sorry, I thought friction kind of like replaced like the M1G sine theta part. So I guess I kind of combined those two. That's what happened.
That's cool. You actually did that right, because there is a component of friction that is part of the weight, but it's the y component. It doesn't say anything about the x component. And it's a good point, because remember when we were looking at it's an easy mistake to make. It's an honest, because when we were looking at motion, remember when we first started looking at two-dimensional motion, and even when we were talking about one object, I did a couple of class demonstrations, I think, to show you that motion in the x and y directions are literally separate and different, even though it's kind of weird to think of it as coming from the, on the same object. But they're two, I think I did it with the thing dropping and comparing that to the thing going over the cliff. And people consistently said that one would hit the ground, faster or something like that. And it turns out they don't, because their y motions are the same. So when you look at this, it's just the same as the object dropping straight down if it didn't have any y motion, any horizontal motion at all. So that's about motion. Here, we can kind of say something related to that about force, is that even though gravity is related to friction, it's actually a separate force from the components. So simply because one of the components is part of inherently associated with the normal force and friction, the other part of gravity is literally acting like a separate force. So you have to account for it. Yeah, so that's how I explain that. But good. But now that you made that error and you pointed it out, you won't do it again, right? So you have to be looking for that. So that's good. That's good. Now the acceleration is up along, is calling up the x direction. Now I'm just going to put something that'll represent the a. So we're just keeping in mind that that's the direction of, of the acceleration. So this is m1. Of course, m2 is just this guy. Put the mass there, point mass. And I've just got, that doesn't change, t up and m2g down, and the acceleration is there. So that's it. Those are the diagrams. And now we can focus on these guys. Red so it stands out. To guide us in the manner in which we apply the force laws. Okay, let's hit it. Net force is equal to mass times acceleration. Well, Mikey, you wanna go for it? Like, how do I write this equation now? Oh, let me do the y direction. So y direction is 0. I'll just do that out. So here's what we get: normal force up, m1g cos theta down, so that the normal force in this case is not equal to m1g, but m1g cosine theta. I think we saw that manifest in your solution already. So you got that. But now, this is what you missed. So let's go to the x direction. Mikey, go ahead. Our net force in the x direction clearly equals m1 times a. But tell me what I should write for the sum of the forces now, and go ahead and make your correction from what you did previously.
Okay, so here we have so in the x direction we have, well, there's three I guess forces or vectors. There's gonna be tension, friction, and then m1g sine theta.
Right.
So F and m1g sine theta are pointing in the same direction, while tension is pointing in the opposite direction.
Correct.
So what I would do to make my correction was I would write equation 5 as T minus F M1G sine theta is equal to M1A.
I'm writing what you said. T minus M, one,
Sorry, T minus F times M1G sine theta.
T minus F times M1G sine theta
Yeah.
equals M1A. Okay, let's take a look at that. This summation means adding them. It's a superposition.
Oh,
Means you're
duh. Right. Sorry.
okay.
So
So
then, yeah, I already know how how that wouldn't make any sense.
tell me, correct it again.
Okay. So we have T. Oh, geez. We got. Would it just be minus F minus M1G sine theta?
Yeah, you're overthinking it. Yeah. So tell me, just to make it complete, so you bake it in. T minus what?
F. So friction. Oh,
Mm-hmm.
what? Yeah.
Yeah.
So, and then after that, would there be another a minus sign?
Yeah.
And then
M
M1G sine theta
equals.
is equals M1A.
Yeah. Awesome. Awesome. Well done. Well done. So that's learning. That's where learning takes place. And this is what you have to do. So yeah. So now and now you think back, whatever your thought was for process before, now it just makes sense. It's a superposition. This means summation. Summation means add vectorially. Add vectorially, now that we've broken it up, means that all the components along the same coordinate direction, we add them up specific to their signs. And you were correct to say that minus F and M1G have to have the same sign. I'm calling that the negative direction because I'm saying the positive direction is the direction of the acceleration. I'm just superposing that on the problem. So my acceleration is positive. So now what we see is that the tension force, not only is it larger than friction, but it's larger than the combination of friction and the component of gravity down the plane. And that's why the object is going up the plane, is accelerating up the plane. So this whole thing now is a positive number, and it's consistent with the way we've written that. M1A is implicitly positive. There you go. So that's the other, you see now it's going to actually have a whole nother term in your final solution.
Yeah, because there's it's right there. I see it. Yeah, makes sense.
Yeah. Awesome. Now, as I pointed out before, we still have a total of 4 unknowns now that we've introduced friction. We've got tension, friction, acceleration, and the normal force. So in order to eliminate friction, we use the definition of friction. So Fk equals mu k times the normal force, but the normal force is m1g sine theta. So you had that term right. When you stick that in, you're going to get that mu k m1g, cosine of theta. So that's where that was. So what you obviously had was just this before, but you missed that whole component. So we then put all that in, and so now we have T minus mu k m1g cosine theta minus m1g sine theta equals m1a. And now you should start to get familiar with these things, meaning, you do these things so many times. There's one thing about, I think I made the comparison of physics to art before. Like I don't have one of these photographic memories. That's not the way my brain works. So when I learn something, I have to bake it in somehow. It has to become sense memory. It has to become, and for me, the only way I know how to do that is repetition. Like I mentioned, the voice thing earlier. I've been playing and singing and writing, music for just as I never pursued music professionally, but I do it. I've been doing it since I was a kid. I think I got my first guitar when I was like 5. But I never pursued profession. But since I got to LA, I've been, especially actually since COVID, I've been like really trying to hone my songwriting skills and think about maybe trying to do something with it. I used to play, before I moved to LA, I used to kind of play out when I was younger in coffee shops and things like that. Kind of feeling like I want to do that again. And just revisiting as an older person, I see a lot of things about my approach when I was younger were, I would say, more objective driven as opposed to artistic driven. Trying to learn a song just to say I could play it and impress people, that sort of thing. But now that I'm older, and I saw no parallel between my abilities, with physics and the way that I approach learning physics than some of the artistic things. In my mind, they were separate things. But as I've gotten older, I've realized that that's not true. At least my point of view now is not, because there's a lot of things I can see that I approach, learning music and writing very similar to how I approach some of the things in physics. And when you think about it, it makes sense because music is just math, right? It's just mathematical. It's just math. It's literally math. Like that's it. There's no explanation. It is math. In other words, so when you write down a song or some sort of artistic, even in a poem, but certainly in music, some emotion, something that elicits an emotion, which then represents the emotional concept like love or hate or whatever. In the score of a song, what you're essentially doing is using mathematics to explain some physical concept. Literally the same thing we're doing right here. But technique and all that is important with music, with playing, right? So, and now I'm seeing that there's an analogy, technique with problem solving. And in the same way, when I the only way I can make a song my own, if it's not something I've written, I've got to break it down. I probably play the thing like at least 150 times in different segments, maybe more, before I can begin to kind of find myself in it. Because it's just so tempting to mimic what, particularly if it's a big, artist, what they've done. And some people are really good. I'm not. It takes me like hours and hours and hours before it finally begins to be my own thing. But I never made the connection that I have to do the same thing with physics. Like when you look at this, I have done these problems so many freaking times in the past 40 years. I just can't even count them. And when I'm studying for a test or something, or when I was, what I found is I had to learn the material and then I had to kind of like practice it. But in the practicing, little things that you were talking about earlier, I think maybe I forget who it was, maybe Kareem or somebody, about how they saw it a little bit different than what I was teaching it. Those kinds of things begin to appear. It's kind of like Neo in the Matrix, right? You're just doing it, kind of going through the motions. The more you do it, and then you're trying to think about every little section, then all of a sudden you just realize things that you didn't before. Physics and music are the same that way. What makes an artist who stays current and original and doing the same song for their entire career and making it sound original is they're always looking at it and improving little things. It never changes. And the thing about music is that it never stops giving. No matter how many times you've said, like you can stop accessing that just by doing it, what do they call it? Phoning in. It's the same thing with any kind of art. Artistic, acting, that's what they call phoning in a performance. So everything is artistic, even if it's science. And so if you kind of have a system where you can look at each section and try to understand what's going on, like you find that as you do it more and more, little things pop out at you that you didn't see before. And it never stops giving. So at some point though, if you're doing these equations, you begin to see the forces. Like initially, when you first look at something like this, it looks like chicken scratch, right? But now you can see the physics there. This is the tension force, the mu k. This whole thing has got to be the frictional force that's contributing to the acceleration. This thing, this mg sine theta, that's always the component down the plane when we set it up that way. So that's the component of gravity, right? Mathematics is a language. Once you start to learn the language, you begin to speak it, right? You begin to understand it. So it's not just chicken scratch. And this is kind of intermediate physics. But when you see any of these, science fiction movies, like they're doing quantum mechanics, like Oppenheimer, because they had a lot of places where they were in the lab, right? And they were writing think they were using Dirac notation, a couple of things that you used to look back there. You look at some of those things, some of that I looked at, it wasn't chicken scratch. Actually, they were had worked out the appropriate problem for that. They weren't just writing equations on the board. Like, they were just a flash or two, you know. And you look at something and it looks like Greek, right? It looks like, how did these people understand this? It's just the same way, like if someone were looking at a score of music and they didn't play music, right? You'd be like, how did someone do it? But clearly people do, right? Because you just start at something basic and you just, do it your whole life, and you do it over and over again, and then it just acclimates. At some point, there's a critical mass, and then boom, you're in, and you can see it, you can understand it, and it just, everything is like that, right? 2 + 2 was difficult when you're in 6th grade. Now, you don't even have to think about it. Well, anything can be like that if you spend enough time with it. So that's what's happening with those quantum mechanical equations. But at this point, with this kind of intermediate sophomore level physics, if you start to practice and just do it over and over again, trust me, you will get a critical mass, and then it will really start to make a lot more sense. So that's why I like to do out the processes every time to show you the clear, because this is how I got to the place where I am. And this is how anybody does. Now, some people may have these photographic memories where they don't have to do the same problem over, 5 or 6 times or whatever when they're studying for a test. I'm not like that. But the thing is, once I do it and I hit that critical point, my intuition, I see a lot of insights that a lot of people don't see. They're separate things, right? Just because you can do the math and have photographic memory doesn't mean you understand what you're doing. Yeah, you can make, it doesn't matter if you want to get a good grade on a test, but when it gets to really understanding, trying to explain to other people, trying to, take that same concept and apply it to a system that no one understands, the intuition is really, that becomes very valuable there. So they're just 2 separate skill sets. And, I was looking at, I don't know if you know this show, but I was looking at this, this new show that's coming on this season, and it's called Skin Wars. And it's about these, they basically went all over the nation and they got the best body painters in the nation, basically, or at least, and it's like 10 of them. And it's one of these shows like that came out, I forgot the name of it back about 15 years ago, but it's kind of based on the show like those designer shows that they used to have, What Do You Wear, or What Something, where they have designers come in and they make clothes and there's a model and then they kind of judge. But this is the same thing, I think it's the same producers actually, because the show is set up the same way, but it's with body painters. And so they give them these different scenarios and they'll have a certain amount of time or whatever to do the thing. And then they have to, they vote on it. So there's one guy who's one of the best in the nation. The guy's amazing. I mean, they're all amazing. But this guy is really technically, like he's the best. No one's ever going to beat him technically. But it's really interesting to show, it really shows how creativity and technical expertise are not the same thing. Because even though his things are always immaculate, I think he's only won one or two times because there's somebody froze. Oh yeah. Because, and I can see it from the very beginning. As soon as he makes the decisions, I can see that he's not making the artistic choice. He's making, everything that he does is basically immaculate in terms of technical precision. And it's also very, very good. So he's not going home, but he's not necessarily going to win because he's so confident in his technical abilities that I don't think he even appreciates what creative insight or creative, what's the word I'm looking for? Inspiration can do. I think he's starting to, now that he's lost a couple of times to people who clearly were not as good as he was, but they put together something that was by no question more creative than what his idea was. So I would use that analogy with physics. Mathematics is an analytical ability and it's a language, and it's a technical thing, just like learning any language is. That's one perspective about it. Just because you're good at that doesn't mean that you know the physics. It doesn't even mean that you're actually good at the physics, better than someone else who is. That was the whole issue with Einstein, actually. You know how there's a rumor that he flunked out of college and that he didn't flunk out of college, but he wasn't the best mathematician compared to the best mathematicians like Heisenberg, like Bohr, like Dirac. He wasn't even close, and he was very insecure with his mathematical bit compared to those people. Where he shined was the intuitive insight, and not only did he shine, he was like 10, 15 times better than anybody else in the world. Something like that. So he kind of made up for it, with, but just to point, and something like Isaac Newton, so far back that it's hard to compare. But honestly, in my opinion, I believe Einstein was better than everybody, better than Einstein, better than he in both math and physics. That's why he's considered the best of everybody, even now, even though people probably won't say that, some people, but he was. There's just no question. And if you ask those people, they will, if you could, in fact, they did ask Einstein, and he said that. And he wasn't just being modest, he was being honest. That's how he felt. And I feel the same way, based on my limited perspective. I just even know, I don't even get on it. But so Isaac Newton is a person who had both at the highest levels of humanity, essentially. So that soapbox is just to kind of say, once you start to move through this and practice these things and start to understand it, I want you to be able to see the differences, right? And to understand what your strengths and weaknesses are so that, you know who you are, know thyself, right? You need to know who you are and know what, so that will facilitate how you approach studying and how you approach getting better. You can focus on the things that you inherently, know what your inherent strengths are and what your inherent weaknesses are, so that you can get better. In my case, the intuition is always stronger than my mathematics. But I've had to work really hard, and still do, get the mathematics to where I'm very comfortable with it. Just like if you were becoming fluent in any language. But my talent is just the insight and the understanding of the physical concepts and how they're related. My natural talent is that. So with that, let's keep it rolling. So here we've got two unknowns, T and A. And we've now exhausted everything for block 1, and we have to go to block 2. So let's go to block 2. Block 2 is still the same. It's just going to be, M2G minus T is equal to M2A. That's not going to change. And so let's write that down. So for this guy, the net force in the y direction, in the x direction, is equal to M2A. And that's going to be M2G minus T equals M2A. And So again, the final two unknowns are T and A. And one easy linear algebra thing to do is just to add equations 9 and 7. A minus T here and a plus T here eliminates T in favor of A. So 9 plus 10 plus, 9 plus 7 is equal to 10. Sorry, I had a dyslexic moment there. So I'll just go ahead and we'll have a positive into M2G contribute here, and that'll replace T here. So we're going to end up having M2G and then minus UK M1G cos theta and minus M1G sine theta equals, And then the two terms, I'm gonna go ahead and factor out the A. So it'd be M2A plus M1A. With factoring out the A, I'm gonna have A M1 plus M2. Getting kind of long there now. Huh? Yeah. Okay, so that's it. That's we're done. Well, we can simplify though. We can well, up here I can actually factor out factor out a G from every term. We'll do that. But here I can factor out an MG from these two terms. So we can write this like this. So A, of course, we're going to be dividing by the total inertia of the system, which is M1 plus M2. And of course, we'll have a G over here. But inside here, we will have, so the M2 will still be by itself. But here we can factor out a M1. And we're going to have the term mu K times cos theta plus, and the only thing that's left is sine theta. Yeah. Now I like to write it like that. I like to write it like that because now we can compare it to, we've done a lot of work since last Wednesday. We can compare it to a couple things. What happens when the angle, so this is my final solution. So you can see your solution is in there. It was basically just this, Micah, but you forgot that last term over here. There's 3 terms there. What happens when the angle goes to 0? Let's do some linear case. When the angle goes to 0, this term goes out. Sine of 0 is 0. Cosine of 0 is 1. So we just go back to M2 minus M mu K, which is the solution with friction and no angle 0. And of course, what happens if the friction is 0? But if the friction is 0 and the angle stays the same, stays non-zero. Well, if the friction is 0, that mu K goes to 0. So this term goes to 0, and I'm back to M2 minus M1 sine theta, which was the solution that we got for the frictionless surface like this. We did that one in class. Go back and look. When we have it at an angle like that, and there's no friction on the plane, we got M2 minus M1 sine theta over M1 plus M2 times G. Go take a look at that. So it's all reducing back to, and of course, when both the friction and the angle is 0, that whole term goes out, and we're just back to M2 over M1 plus M2 times G for the flat plane with no friction. Or whatever. Actually, no. Yeah. Yeah. That was the last possibility. So, that suggests that that's right. And we get the minus sign, so it's still decreasing the friction and doing it even more because we have this other term on here, then when we put the angle down. So going through and just evaluating that qualitatively helps you to understand that this is not just gibberish, it makes some sense and, and it lets you know that perhaps unless there's something else that you missed that you can't see, that this solution is probably right. Now, it's a little bit of a tour de force to go back and get the tension, but I'm going to do it once so you can see the process. And then, for the other problems, if you want to do those, I'll leave it to you to go and do the block leading up. And then also go ahead and do the double block. It's going to be pretty long. I have a lot, but it's worth doing at least once, I think. I've done it once. I think I should probably post it for you at some point. I can't find it though. I did a while back. Okay. Oh, I don't know. I guess I probably will take the A and put it back into this equation. That seems like the simplest one is on. Yeah. Put it back into this guy. Do it once. So now, Mikey, how does that, does that make sense? Working your solution on the acceleration?
Yeah, it does. Yeah.
Yeah.
I mean, like we didn't really add much except for the fact that there's a third term. So like everything else I had on my paper was correct other than that. So yeah.
Yeah. You did. That's right. Good. Well done with that job. Now, these things are going to be kind of long, so erase enough. So I'm going to take the A equation, whatever that is, and stick it back into here. I guess it's equation 12. Now we would anticipate that the acceleration gets smaller, but the tension should get greater by bending it down than when it was flat. So 12. So then T equals, actually, I'm going to go ahead and take these terms over on the other side, okay? Actually, usually I put it in the other guy, but is that easier? That's actually going to be easier. Well, it might be. Into this guy, M2 G minus T equals M, because that's what I usually substitute back into. I'm going to go with that. Sorry, I'm not going to do this. I'm going to put, I forgot what number that was, but I'm going to put A into this guy. That's what I'm accustomed to. So when I flip the minus signs around, what I have is M2 G minus M1 times A, but A is all that. So then times G times this. That's the way I'm going to do it. And again, it's just, I could do it that way, but this is the pattern that I'm accustomed to doing. So when I do that same pattern, same path, it's easier for me to not make mistakes or to catch mistakes. So minus M1 times, if I had done, and also I do think that's just literally longer to do it that way.
Oh, Professor, is that M1A on the far right of like the top equation? Like
It should be M2A. You're right.
okay.
Thank you. So they should be. Oh yeah. Thank you. So you see the kind of my Achilles heel. So that's M2. That's M2. And then I'm just plugging this in, so it shouldn't be any other mistakes. Plus sine theta quantity and parentheses. Okay. I want to first multiply all this out, and then I'm going to add the common denominator. So T equals M2G is still there. Well, I'll take out the G out of everything. So G, okay. So that's going to leave this as M2 over 1, and then minus the M2 goes in. So we're going to get in this thing, we're going to have I'll multiply all the terms out, M1 plus M2. So M2 squared, and then minus M1, M2, mu K, cos theta, and then M2, M1 times sine theta. So plus M1, M2 sine theta. I think we're good. Do that again. This term, factor out the G. This guy, I'm going to get 1, 2, 3, 3 terms it should be. So this term, which is here, then this term minus here, and I almost screwed up, didn't I? Because minus and a minus is a plus, and a minus and a plus is a minus. So that would have been a problem. Right. Almost. So second term, M1, M2, UK cos, and then minus, plus, minus, M1, M2 sine theta. Now, does that make sense before I continue on? I feel like I made a sign error somewhere. Because minus and a minus. I did. I made the sign error right here. These two things should have the same sign. They always do. So why are they different here? Because when I redistributed, I screwed up. That's the same minus sign as over here. So minus, because I factored it out, right? This is a minus and a minus. So that would have been, when I make this plus, it's the same as that. I don't have to worry about it. That's plus. So little things like that. And the other thing is, again, when you're reading the mathematics, I know we've said that both of those forces were in the same direction, the friction force and the component of G, the component of the weight down the plane. So everywhere through all the equations, they should have the same sign. So here, when I gave them separate signs, that's a problem. This is still the component of gravity or associated with component of gravity down the plane. This is still friction. They were in the same direction. They're vectors. So why would the sign change? They shouldn't. So that to me indicates that I made a mistake somewhere, and then I found it. So little things like that, again, also are like some people are just great at that and they don't make those kinds of mistakes. I do. I don't know. It's not carelessness. It's something else. I think I have some sort of version of dyslexia or something like that. I'm not being serious. Like I've been doing this since first grade, and I can't stop. The only way that I can stop is these little safeguards and things that I put in, and then that's why I spend so much time on technique. Yeah. Okay. I think we're good. I don't see anything else. So now we got to add and find the common denominator. That's going to give us two terms, two more terms. I think I can erase most of this now. Erase that too. Something like that. I'll leave that up for the time being. I'll erase it down to here. So I got to find the common denominator, and so I'm going to multiply M2 over 1 times M1 plus 2 over M1 plus 2. So that'll generate two more terms. We'll have G outside. Common denominator will be M1 plus M2. And so then M2 times M1 is M1 plus M2. M2 is M2 squared. So you're going to have M2 squared plus M1 plus M1 times M2. And then all these things. And I think that minus sign is on the outside, right? Did I already handle that? Yeah. That's, oh, I see how I'm writing that. That was really, I should have done it like this. Because I multiplied it through already. Yeah. Multiplied it through already. Right? Yes. So then now a minus M2 squared, and then basically plus M1, M2, UK cos theta, and then plus M1, M2 sine theta. Well, that kind of, I think we're going right, because the M2s cancel out. It goes, I get the standard M1, M2, but then I got these other two terms associated with the angle and friction. And I got the M1, M2 multiplied through each term. So I can factor out the M1, M2. And so now I'm going to have T is equal to G times this quantity in the middle, M1, M2 over M1 plus M2, which has been there for every problem we did. But then times this factor of other stuff. That's going to be a 1, and then a plus UK cosine theta, and then a plus sine theta. And I like writing the solution that way because it's very easy to compare to the simpler scenarios. Let's do. So, of course, when the angle theta is zero, sine of zero, sine of, let's see, yeah, sine of zero is zero. I think it does say, yeah, I didn't do it. Yeah, sine of zero is zero. So it reduces back to the problem we just did, where you get that thing plus 1 plus mu k cos theta on the flat plane. Well, actually, yeah, so that's zero and cosine of zero is 1. So that just reduces back to what we just had. This stuff plus term 1 plus mu k. It's also interesting. I didn't do it over here. Let's do it though. Let's go back to here for a second. What if theta is 90 degrees? I never did that. We know if theta is 90 degrees, the thing should be in free fall. So look, sine of 90 is 1. Cosine of 90 is 0. So that whole term goes out. So basically, that's 1. So that you're going to get m2 minus m1. Did I miss a sign? Because I should get m2 plus m1, right? Because it's got to factor out the whole thing is going at g. Should there have been a minus sign there? I've erased this stuff. I'm second guessing this now. Sine of 90 is, oh, yes, my bad. I didn't go up, I went down. I went to the negative angle. When you go to the negative angle, it reduces to the Atwood machine. My bad. It reduces to the Atwood machine. I didn't go up. If I went up, it would be free fall because it would be full falling. If I go down below the horizontal, the thing is just hanging over one another. So it's the Atwood machine. Sorry about that. And so that is right then, because we did the Atwood machine, I think Wednesday. The Atwood machine is this guy. Right, so we would have like M2 here and M1 there. And we did show that the acceleration for that system is G M2 minus M1 over M1 plus M2. So whenever we go minus 90, sure enough, this is 0 and that's 1. So you basically have M2 minus M1 times 1, which is M2 minus M1. And so it doesn't cancel out. It reduces to this, which is what it should be. It's the Atwood machine. But if I went the other direction, 90 degrees, then yeah. Wait a minute. It's minus 90, so sine of minus 90 is minus 1. So I would have a minus 1 over here. And wait, what? What am I doing? What am I saying? Well, I guess it's how I define that angle, because one has got to be positive, one has got to be negative of the other. So I think I see. Right. Yeah, I have to go. I have to kind of. If I've ever done that in class, I have to kind of go back and show you. But here, whenever we do the angle down relative to the plane, we're going to the positive theta relative to the vertical. So you have to define a, yeah. But then if we go up, then relative to our plane, the angle goes the opposite direction. So we're definitely crossing through a threshold there. I think if I were to think of it like that, then that theta, one has got to be negative of the other. And I think the appropriate thing to say is that here, this would be positive 90. If when I take the angle and do it down like that, when I go from the horizontal up like this, it's actually a negative theta. And so, yeah, if I put negative 90 in there, that's going to generate a negative, sine of negative theta is negative sine theta. Right. Or, is that true, or is it just, I'm getting a little twisted around on the sign there. Sorry. I was spontaneous and came on. I'd have to think about that. I'm getting a little twisted around on my signs on my angle there. But I do know that if you go straight up, the object is just falling through, so the acceleration is going to be g. So you got to set up however you define the theta, set it up so that basically in the numerator here, I'm going to get a m2 plus m1. And the only way that's going to happen, since cosine of 90 is 0, is if I get a negative sign here. So it would have to be a negative 90 to generate a minus sign. Yeah. Yeah, or just 180 relative to the other 90 degrees. That's true. Right. I think I see it now. It's got to be, because when you're at 90, so like when I go to full 90 degrees, like when I go down, the plane tilts like that and the angle is going, so 90 degrees would be, like it's like this thing swings up. And so when I do the other direction, it swings back the other direction. So the difference between those extremes is 180. And it might not be obvious what I'm talking about, but I'm looking at the y-axis and like on this plane, this was the y-axis and gravity, I went down. So yeah, so gravity is like, so yeah, so gravity is straight down. So that's how I had the y component was on the, cosine is here and the sine was kind of pointing along that direction. So the farther I go horizontal, like this angle theta goes from 0 when you're flat to 90 degrees when the plane goes straight down like this. And if I go straight up, it kind of goes the opposite direction like that. So that's a difference of 180. Or you could put in negative 90 for each one, whatever. So I think that's what the case is you got to look at how the component is moving through. And so yeah, when you're going down, it's also moving in the positive direction relative to the axis. The clockwise direction, the counterclockwise direction, which is considered positive. When you go around the unit circle in the counterclockwise direction, that's positive orientation. When you go around the unit circle in the opposite orientation, that's negative. So whenever I take the thing from horizontal to here, it's like, so if this is my y-axis and this is my x-axis, and this is gravity. When I swing the plane up like that, this axis is doing that. But now the direction of my gravity doesn't move. So when I go up like that, that angle is kind of like it's opening up in the counterclockwise direction. So I think that's where I have to get the negative sign from. So that's when I put in negative sign, negative 90, you know, it's just, it'll be a -1 and a minus is a plus. So then M2 plus M1 divided by N2 plus M1 gives me G. So that's what happens when I, you know, when I open the plane up like this, you know, when I'm flat, it's straight down, open up, it does that 90 degrees. When I go the other direction, it opens up kind of in the, you know, the angle is opening up in the clockwise direction, I guess. So that's where we just put in 90 degrees difference. I don't know. I've never thought about this before. I'm surprised that I've been doing this all this time and I never actually, because I would have already worked it out, but I guess I had never done that. I don't know. I never thought about it like that. But like I told you a while ago, you know, when you know what the actual answer is, sometimes you have to kind of adjust the mathematics to make sure you're getting, so that dictates how you should set it up mathematically, right? Because I definitely should get this in one direction and G in the other direction. We've already done those problems. What time is it, by the way? Oh, close. Yeah, so yeah, and so okay, so yeah, so that kind of gives us a limiting case there, you know, with the acceleration. And you can do the same thing here. I mean, but at least we know what we decided is that whenever we shift the plane down, the tension should get stronger, and it does, right? Because we're now adding on. Whenever the tension is just flat with friction, we just have this result. When we put it at an angle, we're adding a sine theta onto that, which makes it even a little bit larger tension when we go down. And if we were to go up, there would be a minus sign here because now you're going to swing. This is what I was just showing you. Right now, when I swing it down the way that I did go, because I've erased the picture, I should put it back up there, but I'm just trying to do it here. So that's when the angle is flat. When I go this direction, gravity is doing something like this. So I have that mg cosine theta along that plane, and that negative y-axis, but I have the mg sine theta that's pointing down in the negative direction. And when we take it over, it makes acceleration negative, it makes the tension positive. That's what. But if I go back to 0 and then go the other direction, look what happens. Now gravity is hanging like this. I'm still going to have mg cosine theta, you know, relative to my axis in the same direction. But now the y component of gravity is actually pointing in the other direction, in the same direction as the acceleration. Tension and acceleration is in this direction. Mg, or the frictional force is still back in the negative x direction. So it's going to flip the sign of the gravitational component along the direction of the x, you know, the horizontal axis. That ultimately will make this a minus sign. So it increases the acceleration, right? Because minus and a minus is plus. So it would be M2 minus mu k cosine theta plus M1 sine theta. And it makes sense because when you tilt it down, it should, you know, it should increase the acceleration from when it's just flat. And then it's going to put a minus sign here. So it increases the acceleration when you go the other direction, and it decreases the tension. And so actually, those are your solutions. Actually, you could look at that, just write the solution out. I would encourage you to go back and prove it to yourself. But if I have this guy, basically I just did it for you, right? If you have that guy, so you did the other direction, the solutions would be corresponding, this guy right here, where this is 2 and that's 1. So this guy is going to be A is equal to G times, I'm going to run out of space. Do it over here. For this guy, you should prove to yourself that A is going to be equal to G times M2 minus M1 mu K cos theta minus sine theta over M1 plus M2. And for the tension is going to be same thing, G M1 M2 over M1 plus M2 times 1 plus mu K cos theta minus sine theta. So these two solutions are going to go for that guy. Now, I did the one with double planes for you. We did that, and we did that with no friction. So, I would encourage you to go do this one on your own to make sure you get those solutions. This guy with friction, but then put the two planes together and see if you can, work through that and get a solution. And if you can do all those things, you can really going to bake this Newton's law thing in, bake it in as to how to apply it and, being on the circumstance. Now, I spent a lot of time on this because I wanted to, okay, yeah, that's cool. Numerical value, most problems, that's cool. Yeah, I don't think you do, but this is just for your studying. Like they're not going to ask you that in Wiley Plus. They're just going to ask you for the numbers. But the thing is, you still got to do. How are you going to get the numbers if you don't do this, right? Like it's almost like it's to your disadvantage because if in face-to-face classes when I give you homework, I don't just look at the final answer, right? I look at all the work and stuff. And usually I have a lot of students like to use this thing, the problem-solving template, to write out the problem, so I can very easily go through and see where you made mistakes, not just, and so I can give more partial credit. For Wiley Plus, is he going to be right or wrong? So you're right. They don't ask you to do all that. And of course, if you have the tension, you get one answer, with multiple answers, you just plug it back in. You don't have to go through and find the analytical solution. But at least for one of the first couple answers, acceleration, whatever you solve for first, you got to do this. I don't know how else do you get the answer. Yeah. So it's still a good thing because I don't know, you could solve for tension first. I don't know what you're going to solve for first. This is just the way I normally go through it. It's always a good thing if you can to it just builds your confidence to be able to do that when you're studying. So just keep that in mind. But you can do it however you want to do it. But that's what I would suggest. Cool. Well, I think that brings us to the end. It brings us to 4:30. I think we did well. So I'm probably going to have to spend a little bit more time on Newton's laws. I'm going to leave this, but I do want to do a couple more different types of problems. I'm going to do like a centripetal motion problem. I'll do that on Monday morning, and then maybe there's a couple ways we can look at that. Put blocks on a playing cards going around a track or something. I got a couple problems that I like to do to kind of illustrate a couple other little things about Newton's laws. But basically, that's it. We're done. And you just got to bake this in, study, kind of go through the homework. I'll give you some time on that. But I want to start working energy. We need to introduce that on Wednesday. And so I'm going to go ahead and open up those chapters. And I guess this is week 7. So open up those chapters and the quizzes and things in the modules. But continue working on Newton's laws. Probably prepare for a test. Probably need to have the second test. We need to, probably could this opening it, I mean, we don't do it on a different day, so it's not as much pressure if you have to do it on a day. And this second test will also be an at-home test. So I forget, I don't know when the homework is due, but probably we'll open up the test, either this Friday, that's kind of soon, but maybe over there. So I do want to give you a couple days to do it. So usually it's good. I like to open them up on Fridays because but you don't have to do it and give you a couple days to work on. So and the weekends are usually better than other days. But I think I already have the date down. I'm hoping I'm keeping up with that schedule because I put the dates on the modules. In fact, let's take a look and see when that is. Look at the syllabi real quick. Because that's what I'm going to try to stick to. But remember, on the module, I told you they can fluctuate within 48 hours. And this is why. Because pacing can kind of fluctuate just a little bit. So let's go to Canvas. And why is it doing that? Okay, slow. And then we'll go over here. And we go to, this is your class, yes, go to modules. And put the syllabus here. Here. With the updated syllabus, I believe I got it straight. That's straight. Yeah. So test 2, chapters 5 and 6, 10.4 and 10.6. Oh man, we already passed that. So 10.6 would have been last Friday. Yeah, so I have to adjust that. I think because I don't know why. So we'll have to adjust that. I have to make it, I think I'll have to push all these test dates back a week or so. So I am going to open up test 2 on Friday. Need to go ahead and get that out of the way. And yeah, because you gotta stay on this pace. But I mean, that's like I open it up. You can turn it in on. I said on the next on Monday. Yeah, so either I might do it. Give you the weekend plus a day. But so stay on top of things with that. Okay. All right. Any questions, problems, troubles, and or gripes?
I had a quick question about the lab.
Yeah, Raheem, how you doing today?
Good. How are you, sir?
Good, good.
For the second chart that you want us to make, the one that shows force by acceleration,
Yeah.
did you did you want points on that graph, or was that supposed to be a line?
Yeah.
guess I
So
could
with
start-
those, yeah, I haven't spent a lot of time talking about this since it's just the lab exercises. So basically, it should be you're going to get something like this, right? It's going to be technically if this were real data, we would be doing something like linear regression. So if you have F, was it F versus what?
acceleration.
Was it acceleration? Okay. Well, you're going to get a series of data points, maybe something like this. But technically, linear regression gives you the average value of the line. So I definitely don't want to see you doing something like, like this, right? That doesn't make any sense. So, I didn't teach you the linear regression. Does it ask you to for the
No, it's
average
not asking for linear. I think I see what it is, or what it's trying to make us realize. Because I think the force over acceleration. So it seems to have a, okay, so and it's for the first three experiments where the mass of the object was the same. So the slope is just pointing to the mass of the object.
Yeah, because normally with that, I don't remember what the, but yeah, it's just giving you it's showing you that if that's what the case, I don't remember what that particular thing was asking, but because normally you're F versus, X, but we haven't even gotten there yet to do friction. There's something where you can do
Yeah,
that.
no,
But
I see it now. I think I see the relationship. There's a direct correlation with the slope to the slope is just
mass.
pointing at the mass of the object.
Yeah. So if you calculate that slope, F over A is going to give you mass, and that's consistent with Newton's second law, right? F
Yes, it
equals
is.
ma.
Yeah.
So it's just showing you that that's why
In the
even though
chart
we have
before that, to solve for acceleration, we did F equals ma, and then we put A equals to F over m, and that was giving us the acceleration. So this is just showing it to us in terms of the mass, the relationship to the mass. I see what it's doing. Yeah, I
cool.
think
Awesome.
yeah.
Awesome. Well, I'm glad that answered that. That's awesome. Yeah, cool. I mean, that's one reason why. I mean, these labs, they have some value. They're actually pretty good. If we were actually doing them in real time, they would be really great labs. These are the kind of lab, but they're pretty good. They point out these little subtleties. So I think I might actually keep them as exercises or some degree, even when I go back to face when we're doing the real labs, because there's some value in thinking through these and working through those little. They're kind of fun once you get accustomed to.
Yeah, I was having trouble
labs like we're
realizing
doing.
it because I think I was trying to do it like the way we did it in the last lab where it was just showing like acceleration is constant, but I don't think that's what what the question was trying to make you realize. It's you're graphing the points of the first three experiments, and then when you look at the slope, you realize it's just the slope is directly pointing to the mass of the ball or the object.
So
So
what it
that
has you changing the mass for the three different experiments for putting different objects on there with different mass or something?
yeah, but what the instructions were it was we used Newton's second law, and then we calculated the acceleration two ways. We used delta v over t, and then doing it by using Newton's second law, which is force equals mass times acceleration.
Yeah.
And then for the graph, it said take it says draw a force versus acceleration graph. Just use the first three data points. So I'm assuming it means
I see.
the one where all the experiments were just 2 kilograms for the weight.
Mm-hmm.
And then because of that mass, when you plot this, the force and acceleration, it's the line, it's linear, it's a straight line, and the slope is 2, which just points back to the mass of the object. So that makes
Awesome.
sense. Yeah.
Good. Well, I'm glad you answered that for yourself. Awesome. And that is a true statement that the mass is the mass is the ratio of proportionality between the force and the acceleration for an accelerated body, according to Newton's second law. Awesome.
Thank you. Yeah, I guess talking through it helped me see it a little bit. I was just staring at it last night and I couldn't figure it out.
Cool. Well, that reinforces that these labs do have some value, even though they're not the best kinds of the more conventional labs, but they have some value. Okay.